Welcome everybody to the final day before spring break, week 11, day 3. You had it done but kept segfaulting. Yeah. I'm going to do something a little different. We got zyBooks due on the first day after spring break. I'm not going to do what I normally do and give a homework assignment over spring break. So enjoy your break. There's going to be zyBooks, but whatever. It's just reading. You don't hear me? You don't hear me? Test, test, test. No homework over spring break. I'll type it for Yoxtheimer. However, what I will do is give all of you guys a bonus last chance. So if any of you guys have missed any of the homework assignments, do it. Message me on Discord before the start of class on Monday. Okay? So, any of them. Yeah. Any of them. So, any bonus last chance. One time only. By Monday after spring break. Do any of your missing assignments. Message me on Discord. I'll manually regrade it and give you the points on it. So, not going to give you guys homework, but I really want you guys to understand the material. So if you don't know linked list, or rather if you didn't know linked list when the linked list assignment was due, and you understand it better now that you've done the competency exams and stuff like that, go back, hit it up. I want you guys to get, I don't want to fail you guys. I want you guys to know the material. So demonstrate to me that, can you do Farkle next? Ooh. All right, so Muya is proposing doing Farkle over spring break. So what was all that you just said? It's right here, Yoxtheimer. Right there. Okay. Is it only missing? You can bring your grade up. Yeah, if you're missing points or whatever. Yeah. One assignment. One assignment. My mercy is not without limit. One assignment. Bring your points. Okay. Please not over break. I don't know. I mean, if your TA asks for it, Maddie, it's cancel Muya. All right. Yeah. All right. Probably should be typing that in the Unix prompt, but whatever. What about the bonus zyBooks? Yes. Good point. So there's zyBooks due on Monday after spring break. I also put up a bonus zyBooks. It will substitute in for any of your missing zyBooks assignments. It's on balanced BSTs. Like I said, balanced BSTs are a topic for junior level computer science. We don't cover it in this class, but there's a chapter in the zyBooks for it. So I'm like, hey, we'll just do that extra credit, and then you guys will, even though you don't have to code it. Coding it's the hard part. Understanding it's not so bad, but coding it, is kind of annoying. Although I did TA that class enough times unofficially because I don't think I was actually paid for it. But I TA'd enough of my friends through making red-black trees that there was a point in my life where I could just be like blindfold, make a red-black tree. I have not made one though in ages because I use the standard library. Right? Because back in the day we didn't have the standard library, or rather, when it was a standard library, but we didn't have the standard template library. We didn't have this nice templated set class that we could just make and then like insert into. You had to make that stuff yourself. Every project you had to make it yourself. And if your binary search tree had a bug in it that only happened once every 100 times because you had to use after free or something like that, guess what? All the programs you have that use your own Kearney BST in it crash 1 out of 100 times also. It's a real pain. That's why having a good standard library is really important. You want common tasks to be simple and bug-free. Okay? So you only see the X credit zyBooks, no other one. Really? You don't see the regular zyBooks? Canvas sometimes doesn't save it when I publish something. It's kind of annoying. Sometimes it doesn't save it when I unpublish something either. That's more annoying. It's like I'll have stuff left over from the previous semester, and not this class, but in other classes, and I hit publish the module, it automatically publishes all the things in it, and I go through and unpublish them. And sometimes that doesn't take, even though it shows it as being unpublished. I refresh the page and it shows the green check on it again. So let's take a look at it. Yeah, what happened to it? Okay. All right. zyBooks, week 11. There we go. So the assignment existed, it just wasn't added to the modules. Yeah, that was my fault, not Canvas. Okay. So they're up there now, and we're on week 11, day 3. All right. So before we begin, any questions about Dungeon Delve? It was doing your own binary search tree, but only for the inserting and searching parts, which are the two easy-ish operations. No deleting. Yeah, deleting's annoying. Like I said, to delete something, there's like all these different cases. It's the last node in the tree. You have to clear root. You have an empty tree, do nothing. If there's one kid, you delete it and set the parents' pointer to null. There's 2 kids, and you know, yeah. Did I post the study session recording yet? No. Could you link that to me, and I'll put it up on Canvas right now. So deleting's kind of annoying. I'll give you guys that. It's kind of annoying. I'll probably put it up on the code it for the competency exam. You got 20 minutes. Go. Make any mistakes. 0. No, I'm not mean. But there will be a BST competency exam afterwards. There's not going to be a competency exam on stacks and queues. I'm sorry. They're so basic that it's like, yeah, I don't know what to tell you. Like, they're just really simple. So, yeah. Any questions about Dungeon Delve? I noticed that a lot of you guys got a 0 on it, so I'll put up a thing here. Page. Spring break, super fun party, extra credit. Okay, it's not a party, but if you are missing points on any of your individual or pair programming assignments, you can redo it, and message me. I will regrade manually and give you whatever points you deserve, which is 0. No, I'm kidding. All right. Yeah, whatever points you deserve is probably not the right word. Whatever points you earned. So this won't count as your last chance. So if you've used last chance, you can do this also. If you haven't used last chance, this won't use your last chance. Okay, that fair? The deadline for this is from noon on Monday, the April 5th. April 5th. Yeah, please don't message me after the thing, because it's like, you got all of spring break to do it, you know? If, like, your dog bites you or something, like, you know, an hour before the deadline, it's like, well. So, there we go. So spring break, super fun party extra. There you go. Nope, not grades, not grades. Don't show that. Reveal who the top student of the class is. How do I submit a picture of the visualization in the link? It is on the thing, right? Like Dungeon Delve. Edit. On Canvas. you submit the link. Your cat messes up your code? Yeah. Cats love being in the action. Moya, did you send me the thing? You did. Cool. Copy link. Come down here and do that. If you guys all, could you guys all give like a clap emoji at Moya? Like he doesn't need to go above and beyond for you guys, but he's, you know, he is, you know, doing study sessions, extra study sessions for you guys, helping out on Discord late at night. And we linked list. No, not linked list. Sorry. Classes study session for classes. Complex exam take 4. And the secret password is in there. Okay. So in order to get the password and unlock competency exam take 4 on classes, you must watch the study session. Okay. I guarantee you will not be able to guess what the password is. So, Benninghofen. Okay. All right. Nancy Pelosi. Petition for a raise for Moya. Sorry. It's communism. Everyone gets paid the same. They pretend to pay us and we pretend to work. Okay. Yeah. It's neither 42 nor is it Harambe nor is it Harambe 42. It is an ultra top secret password. You just have to watch a study session if you want to do take 4 in classes. Okay. So far, a couple of people have turned those in. Make sure that your constructors are correct. That's a common mistake that people have been making, is their constructors aren't written correctly. So pay extra attention to that. But you should be able to spit out a class, a properly designed class. You should just be able to knock it out. That's the level of proficiency that I want from you guys. Okay. All right. All right. So here we are, last day before spring break. Is the visualization graded in PuTTY when you auto-grade it, or is that separate? That is separate. So what I do is I enter the scores from PuTTY, and then I go through Canvas and see who submitted a visualization. I click on each of those. That's why your grades aren't in Canvas yet. I was just looking at the grades. But I need to go through and see who did the visualizations. You lose points if you didn't do it. Okay. Yeah. All right. So no questions about Dungeon Delve? I'll show you a little slice of how I did it. Dungeon Delve.reference and pull it to the side, so don't reveal too much. Tree.h. I will give you my search algorithm. So that's the whole thing, right? So there is only two, like my whole implementation is 46 lines for the BST, right? So search returns true or false if the thing is in the tree or not. And then I've also got a parameter called noisy. It defaults to off. So if you search to see if the letter C is in the tree, and you just pass in search for C, it'll return true or false. It won't be noisy. Remember, default parameters like this are a nice way of making two different versions of a function without having to copy and paste your code. So some of you guys I saw had a version to search your tree to see if something was in it, and a version to search the tree that printed out the directions, and it's like, just do this, one version. And then basically, it's a standard binary search research. If the letter we're looking for matches the node's data, then we print out found the letter C, whatever, retrace your steps to the entrance, and it returns true. Either way, whether it's noisy or not. If Otherwise, if the data, if C is less than the current node, we go to the left. If there is no left, then it's not, the letter is not in the tree. Otherwise, we print, take the left door, and then we recurse down to the left. Otherwise, if we don't have a right kid, return false, not in there. Otherwise, print, take the right door, and recurse to the right. That's it. That's how you solve a dungeon. It's not too bad. Okay. So Muya says that's inefficient. What is inefficient? My code's inefficient? How dare you, sir? It's quite possible. Like, especially when I'm writing code that wants to be readable. Not my code. Okay. I don't think there's any faster way of doing this in terms of like big O. If you were trying to go for absolute speed, probably you would. I would do it like this. Okay, so here's a good question. How could I make this faster? Big O wise, I don't think I can make it any faster, right? Because you just got to go through the tree. You know what I mean? So if worst case scenario, it's order n, because these trees are not balanced, right? So a balanced tree, this would be an order log n algorithm. But how can I, from a practical standpoint, make it faster? Muia's like, yep, there is a glaring issue in there. All right. Well, don't reveal it. Let's see. Not taking X by reference. Okay. In this case, it's characters, so it's faster to pass it by value, actually. Because if you pass a char by reference, you pass a pointer to it, then it has to dereference the pointer. It's one extra step. You're not going to notice any difference in speed. But it's actually technically slower to pass a int by reference because there's a level of indirection you have to go through. And worst case scenario, you actually get a page fault. It's probably not going to happen though. But it could actually be substantially slower if you pass it by reference when you don't need to. So for primitives, remember the rule, guys. The rule is primitives pass by value, objects pass by const reference by default. That's the default. The default rule of thumb. Exceptions do exist. Right? Like if you need to change it, you pass it by reference. You know? Anything you are going to change, pass by reference. Not const reference. What are primitives again? Int, float, char, double, short, long, unsigned long, uint 64_t. Any of the built-in data types. Not a string. A string is an object. Yeah, good question, Emma. Very good question. Yeah, a string is actually a class, and so you want to pass strings. There's the string class. String is actually not part of the C and C++ languages. It's actually, you actually have to include it for it to exist. Can I do a \n instead of an inline? Yes, and this is faster actually. So having a \n is actually faster than double left arrow inline. Inline, when you do this instead, that actually does what's called a buffer flush. And so it'll actually synchronize the output buffer with the screen. That actually can be fairly slow. Like you can actually slow down your code substantially if you use inline instead of \n. If you're in like a hot loop that's running millions of times a second, you definitely want to pull out those inlines and maybe only do it when you're done with the whole thing so that the buffer gets flushed. Or not. Just, you know, using... I use double left arrow inline when I'm worried the program's going to crash. If the program's going to crash, you want to use double left arrow inline. Why? because it syncs the output buffer and it makes sure that words appear on the screen. If you use \n and your code crashes, it might actually not display what was supposed to be displayed. \n is faster than inline. Yes, it is. Double throw inline is nicer to type, I guess. It's 7, 8 characters instead of 2. So normally my rule is if I'm ending a quote, then it's \n. If I'm not ending a quote, like if I have like a double throw y, then I follow with inline because I don't like typing. I don't like typing that. It's faster to type inline. So the only way the program knows it is a pointer is just because you're dereferencing or using the arrow operator. Does that mean I could say int x equals number and then dereference that? You could. You shouldn't. The C++ type system doesn't want you to do that. Right? Like you could say int x equals 0, float pointer putter, as what's his name says it, Arthur Dwyer. He calls it putter, auto putter, smart putter, unique putter. He's a good guy, but it is funny. Okay, so equals, I'm going to cast this to that. Oh, I've already got x. Damn. So hard to come up with variable names. All right, there we go. So casting to float. Fine. Long. There. Okay, so yeah, you can do it. Okay, and if I were to see out the value at the pointer, I'm gonna start calling it putter too. if I see out the value pointed to by pointer, putter, whatever, what value is this gonna print? Putter. Incorrect. But don't allow my saying it's incorrect to dissuade you from talking. You should talk on Discord and be wrong. Take it. You're not getting marked down for this. This is how you learn. You learn by being wrong. Story of my life in Japanese, man. I tried on a midterm a new sentence style that I never done before, and did it wrong, but now I learned it. You learn from mistakes. It's not a big deal. We've trained our students these days to be so terrified of making a mistake that they would rather sit there quietly on Discord and just not participate. But you're not losing any points, through guessing and getting it wrong, you learn. Trust me, every time I've lost in a tournament, in like martial arts, I remember how I lost. You remember your mistakes a lot more than you remember your successes. And if you're not losing any points, then go for it. Okay. Dereferencing null pointer, so segfault, correct. Putter is, damn it, now I'm doing it. Point PTR is holding the memory address of 0. So is equal to 0. 0 is null. 0 is null pointer. Okay. This is a very convoluted way of saying mistakes make you stronger. My dad when I was born. That's funny. Yeah, so this is just a very convoluted way of setting a PTR to null pointer. And so if we try dereferencing the pointer, this is the dereference operator, that says print the value at that memory address. What's that memory address? 0. Death. Death is there. The minefield of doom awaits. And so if I were to try to run this code, it would segfault 100% guaranteed. 100% guaranteed. So if you're still not comfortable with pointers, practice. How do you get to Carnegie Hall? Practice. Okay, so there's my clue for you guys. Yeah. There's the rule of thumb. Okay. Not going to save it. Int pointer is a different primitive type than int. Yes, it is. And C++ does not like you doing that, right? Like, there's a type system in C++ for a reason. And ints and int pointers don't normally interact with each other. But under the hood, if you look, when you take assembly, you realize everything's an integer. Functions are just integers. Like when you call a function, it's just an integer. What? You know, I thought I was calling, you know, cout or something. No, just an integer. You know, here's all the functions in a.out. You can see C++ does this name mangling nonsense. Well, let's see if, here we go. I got a function here called foo. So when I call the function foo, foo is at this memory address, 0001289. So when you call the function foo, all it does is say, go to that memory address and run the code there. That's all it does. So, yeah. Functions are just integers, man. It's all just integers. In this case, 64-bit integers. So, something about tx not by reference, but obviously Kearney was right. Well, okay. No, actually, Muya, you were correct, because it's t. My code was t, right? Not t reference. Ah, no! Damn it. Now we're going to have students, like, replaying that part of the stream. Zooming in. Yeah, so this could be by reference, right? Then I'd lose the ability to put a literal into there. Like I couldn't pass in 5 or whatever, or 10, or a. So, yeah. Probably, I don't know. Probably should make a const reference. I don't know. You know, it's one of those things. Like in reality, this class is only going to be used with chars, and so you know, probably it's a valid criticism. It's a valid criticism because this is basically is going to be right. So there are things you can do in C++, like enabling and disabling different parts of code if the template parameter is different. But that was not what I was going at for the optimization. But it's a valid criticism. It's a valid criticism. Somebody's screen cap. I'll have to go through the YouTube and cut out that section. There's no reason to template this if you are doing it with chars. That is correct. You could just make your tree class take chars. And that's all you need for this assignment. But like I said, I'm trying to teach you guys proper technique. And if you're going to make a tree class, you might as well make it work with everything, right? Anything that has a less than operator on it, right? That's the only thing that T needs to have. T needs to have a less than operator. It needs to be comparable. That's why I use the less than operator, not the greater than operator. Why? Because most people only do the less than operator. When you make a class, the first operator, and oftentimes the only operator you make is the less than operator. Because that will allow it to go into the set class, and that will allow you to sort it, and stuff like that. So everything requires less than. Not less than or equal to. Not greater than or equal to. Less than. Sometimes double equals. So, how can I speed this up? If this is my hot loop, the hot loop is, you know, where you're calling it millions of times a second, 90% of your time is being spent in just this one function. You have perfed your code. Perfing your code means to perfing your code means you've analyzed where it spends its running time. Right? And so if you have perfed your code and your perf tool says 90% of the time in Dungeon Delve is spent in this one function here, then I would probably be like, all right, I'm going to optimize it. If it's not, nah. Nah. CSI45 needs to know this. Yeah, CSI45 you actually get graded on your runtime. In this class, you don't. You get graded on correctness most of the time. So what can I do? What can I do to speed this up? There's two obvious, well, to me, obvious answers here. Asks somebody from CSI 45. 45 is assembly, yeah. We still write C++ code, but it intermixes with assembly. Rewrite it in assembly? You could, I guess, yeah. Not in this class. Make sure all the characters and password are actually in the dungeon before you call search. Yeah. Okay. Can you remove the if statements that call for noisy? Yeah, you can. So what I would do is actually do what I said I didn't want to do. Yank, Shift 5, Shift P, YY, P, there. Have noisy search. Right? And then delete all these if statements. Because they're called in two completely separate cases. The regular search is called to vet the input, to make sure that the solution you're looking for has all of the letters in the tree. I'd never need it to be noisy. And so I could split this into like noisy search and like quiet search, right? Wait, shoot. Noisy, yeah. Easy fix, noisy search. Quiet search. Okay. And so for noisy search, we can just always see out the things. And then noisy search also, we don't care if it's actually in the tree or not, right? Void. Because by the time we do the noisy search, by the time we get to the noisy search, we know it's in there already. So we actually don't even need to check for the end of the thing. You. There we go. So now we've got two different versions of the function. If statements are actually surprisingly expensive. They can be. They don't have to be, but they can be. So an if statement can take as much time as like 8 additions. Okay? Depending. And so by getting rid of the if statements, so I got rid of all of the if statements basically in this one, inside of the loop here. We had 2 before. I got rid of both of them. Here we still need that, but we don't have the if noisy, so we have streamlined the code substantially. Now, you can combine them using a template parameter. What? Yeah. Huh? So I am going to go and do an even better. Ah, no!
What?
No!
What? 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 What?
It's revealing the answers to the students, Ada. Danger.
What is revealing the answer to the students?
Briefly on the screen, it showed the answer. Students.
Did you see it?
Because when I relaunch Vim, it doesn't restore the screen where exactly where it was. No.
Guys?
Don't help him. Don't help him.
No, I was going to type in say yes. This is a yes.
Just don't use my code. How about that? All right. I know it's on YouTube, right? So just don't use my code. All right? The cheat checker will pick it up. So you can use my search code. Don't use the rest of my code. Okay, you guys understand honor system, right? Yeah. Okay. Damn it, Vim, hoisted by my own petard. Yeah, they don't have to see it, Ada. This is recorded and up on YouTube, so all they have to do is rewind to that 1 second. You know, look at it. Yeah. Did any of you see the answers? Okay. So. You don't want to know how many students Kearney has exposed for cheating. Yeah. It was too quick to read, I know, but it's on YouTube, frame by frame, you know. My daughter is asking if you guys saw the answers. Okay, all right. So let me show you guys how to do something cool. Something cool with templates. So we can template bool noisy.
Good, we have a yes.
No. All right. So look at this. Look at this. This is interesting. What did I change? What did I change? I'm not going to show you where I'm calling it. Perhaps. Perhaps. What did I change? You clicked on the image. It's a cow saying perhaps, girl. It's not going to do anything. So what did I change? How will this be faster? Well, it won't be right now because it's still got the if statements in there, right? But
Oh, wait.
So, Ada.
Okay, he did see the answer, but he already finished it on Wednesday.
It's not taking two parameters now. It's taking one parameter, but it's taking a template parameter. And so what this will actually do is in main, what I'll have to change main 2. I'll have to say search true, you know, searching for the letter A or whatever, right? So before, yeah, I know it's not valid. Thank you.
Guys, be honest and do not rewind to that point where he actually
Thank you, Ada. Thank you, Ada. So what I had before was this, right? Before, it was like search for the letter A and be noisy. This is the before. And then the after is going to be this. Okay? So what's the difference here? Well, when you do a template, it actually will generate different code. And so I can actually have based on the template parameter, actually have different code generated by the template parameter, right? So I can have what's called here const expr if was it const I haven't done that in a while, but basically you can turn on and off chunks of code based on the template parameter, and then so it will selectively generate. It'll essentially generate those two versions I had before, the silent and the noisy version, but you don't actually have to have two different functions to do the same thing. When you make it a template parameter, remember templates generate code for you. And so you can just have one function and use the template parameter to generate both versions. It's pretty cool. All right, so that's enough of that. What do we got to talk about? Hash tables. We need to talk about hash tables and why hash tables are awesome and how they're neat and how they work, stuff like that. All right. So what was the big idea, main topic for today's lesson? End of part 1, begin part 2. What did we just talk about for 45 minutes? That's a good question. We talk about heaps as well. Yeah. I never learned the template thing he just did. Yeah, yeah. There's a lot of things you can do with templates, and we're not going to cover them in this class. If you're interested, you can look up something called template metaprogramming. It's really cool stuff. That's considered advanced C++ though. So, and yeah. Did we review and went over these? Yeah, we went over Dungeon Delve. Okay. So now we are going to go over hash tables and heaps. All right, so go into the CSI 41 directory here, new page, 32621. All right, so hash table. Hash table, the most basic way of doing a hash table is you have an array, and you're going to insert some value using a key, or if you want to be super basic, have the key and the value be the same thing. So like, let's say we're going to insert the number 51 into a hash table of size 10. So this is a size 10 hash table. We're going to insert the number 51 into it. What slot does it go into is determined by what's called a hash function. And there is a standard library hash function if you're curious about it. The most basic one, of course, is to modulus it. Okay. So what is 51 modulus 10? Go for it, Bazookin. All right. So yeah, slot 1. We check slot 1. Slot 1's open. Sometimes you can represent this using a bit field. 0, 0, 0, 0, 0. None of these are filled right now. Or sometimes you use a magic number. Negative 999 means it's open. I don't recommend that. What if somebody tries to insert negative 999? Code breaks. I actually did that in, what was it, like my first graduate class, or maybe my last undergraduate class, somewhere in that time period. I had a thread manager that was doing multi-threading, all this stuff. And rather than returning 2 values, which was annoying, because it's multi-threaded, I didn't want to use a global to return a value, because then if you have multiple threads returning at the same time, they would overwrite the global. And I was like, you know, I'm just going to use a match value. I don't care. And so I just picked like negative 1 million. So when the function returned, if the number was negative 1 million, that means an error occurred, and the thing would pick that up. Otherwise, it would use the value. And the professor fuzzed your input. It would randomly generate input for your threads, and one of the inputs turned out to be negative 1 million. And it wasn't even negative 1 million. It was like something obscure, like negative 257, whatever. And his random number generator picked it up, and I failed a test case because of it. It's really annoying. It was bad coding on my part, but yeah. So 51 is going to come into here, and we can set the bit field to be true. Okay. So, too much. There we go. And now, let's insert. Give me another number to insert. 26. You wanted me to insert 26. Okay. All right. So 20. What is 26 modulus 10? (26 modulus 10 is 420. 26 modulus 10 is 6. Right? You guys don't know what modulus is? It's the remainder operator. So 10 divides into 26 2 times with a remainder of, that's modulus, the remainder of 6. Modulus, very useful stuff. Okay, so 26 will go into slot 6. All right, give me another number to insert. Big O cheat sheet. Yeah, that's fine. Big O cheat sheet. Yeah, I think I've actually displayed this before. The trouble is, like, the cheat sheets don't help you, right? Because you have to understand what's actually happening, right? Like, here it has inserting and deleting from a singly linked list being order 1. That's wrong some of the times. If you're inserting in the middle and you don't have a pointer there, it's order n, right? You know what I mean? Like, you know, inserting and deleting into a stack and queue are order 1. Okay. Inserting and deleting into an array is order n. So that's assuming you're not inserting and deleting at the end. But here for the linked list, it's assuming you're deleting at the beginning or end, right? So they don't even have vectors on here. But vectors are basically arrays. Yeah. So, you know, it's useful. It's useful. But you actually have to understand what's happening when you insert into a linked list. You have to understand what's happening when you insert into a binary search tree. Is it a balanced binary search tree and unbalanced binary search tree? It doesn't say so here, right? Right? This, okay, worst case time order n. Yeah, so that's not the binary search trees we use in practice. In practice, we use a red, okay, fine, a red-black tree. Fine, okay. In practice, we use red-black trees, but you know, your binary search tree for like Dungeon Delve is in fact order n, and most of the time it's going to be order log n if it's a regular average data set. There's hash tables, yeah. So it's a good, you know, it's a good reference to have, but if you're memorizing these things, you're going about it wrong. You're going about it wrong. You need to understand the data structure first, and then when I ask you a question about it, you should be able to generate these things. You know what I mean? It's like when I was in physics, I learned that the reflections off of cars were polarized horizontally, vertically, horizontally. One of the two. I don't know. Now it's been too long, but and then sunglasses are set up to filter that out. Their sunglasses are polarized the other way. Cool. And so I told that to the electrical engineers that I was working with that specialized in optics, and they thought about it. They're like, "Oh, is that true?" And they think about it, and they're like, "Oh yeah, it is true." because they actually understand the principles of how polarization off reflections works. And so they sat there and they thought about it, and they're like, oh yeah, that does work. And see, for me, it was just a fact to memorize. And now I don't know which one it is. Is it horizontal? Is it vertical? I don't know. You know, I know it's one of them. That's all I can tell you. But, you know, their knowledge is better than mine because they understood the principles that go into it, you know? So, next up is going to be -7. Oh, -7, you say. All right, so -7 modulus 10 is what? Let's see if a Windows calculator is still bugged. Switch into programmer mode, and we've got here -7. -7, thank you. -7, where is the modulus? Modulus by 10 is -7. Ha! Wrong. Wrong! When you do a modulus, you're supposed to get a number from 0 to 9, right? So, a university needs me as a professor. Some professors don't know how to teach and just say, where do you think I'm working, Wyatt? You should be a professor. Killing me, dude. Killing me. All right. I mean, a real university. Yeah. Or are you talking about? Oh yeah, that's fair. Damn, Kearney, you should consider teaching Seaside. You're pretty good at it. Yeah, thanks, man. That's funny. Okay, so yeah, -7 does not give by Windows calculator. If you punch this in, it does not give you a number from 0 to 9, so it's wrong. So 3 is the right answer. Negatives. Yep, you got an eraser on here. I'm just giving you a hard time, Wyatt. It's fine. Yeah, I do look askance at how some people teach, because I don't think memorization. You know, in Japanese, you're going to memorize vocab, like that's fine, but you know, when you understand principles, then it's easier to understand principles too, because it's a lot less to memorize. You know, and then you have a deeper and better understanding of the material. So -7 is going to go in here. All right. So what else? What else? Give me another number. $61. All right. So let's insert 61. It's improv hash table theater. We're going to insert 61. Okay. Here we go. And so let's say we've got these bits set as well. So it's true, and that's true. Okay. So let's say we're going to insert 61. 61 tries hashing to slot 1, just like with 51, but the spot's taken. Oh no, spot's taken. So this is where hash tables differ. So hash tables differ based on how they handle collision. Collision is when two things collide. Collision is when two different values map to the same location in the hash table. And so this is where hash tables differ. And so there is 4 different common things that I'd probably teach. First is linear probing. I don't know why there's an extra L in there. Probing, linear probing. So how does that work? With linear probing, if 61 tries to come in here and there's a spot, you go to the next spot. 61, done. Okay. Now, let's say that we're searching for 61. When we search, we come here, it's not open. If it was open, we'd return false. Like if we were to search for the number 10, 10 goes to an open spot, it's not in there, return false. Cool. If we search for 61, it's not open, and it's also not 61. So that's our third case, so we have to worry about it. It's not open, it's not the right answer, so we move to the next spot. We found 61, return true. What if we were to search for 81? If we were to search for 81, 81 would hash to here. It's not open, it's not 81, go to the next one. It's not 81, it's not open, go to the next one. It's not 81, it's not open, go to the next one. Ah, it's an open spot, return false. Okay, and so hash table performance, as you can imagine, gets bad when it fills up. So if we were to fill up this whole thing, let's say we insert 1, and then we insert 11, then we insert 21, then we insert 31, then we insert 41, then we insert 71. Now, if we search for 81, it's going to go here, not open, not 81, go to the next. Not open, not 81, go to the next. Go to the next, 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 go to the next. And we've come back where we started. Notice it wraps around, by the way. It wraps around. Okay. Using the power of modulus, right? So when we get back to where we started, then we know that it's not found, right? And so hash tables have order n, insert, search, and delete if they're implemented in this fashion. Okay. So wait, I thought you told me hash tables are order 1. Yeah, it's because if you use the smart hash tables, they reallocate when they get full. You know, smart hash tables get bigger. They grow like a vector. And so they can keep themselves relatively sparse. Okay. And so there's usually what's called a load, like a load limit, that when you get more elements in the thing than the load limit, then it does the vector, doubles in size, copies all the elements over, and now the load has dropped in half. So the load limit is like the percent full. Okay, so yeah, so, but if you were to do it this way, it'd be order n, right? So again, it's a matter of, do you understand the principles, right? So if I were to search for 31, do you guys see how this would work? If I were to search for 31. Smart hash table is an update to hash table. It's the way the standard library does it. So the standard library has, on average, order 1, insert, search, and deletes. But if you do it this way, it's worst case, order n, if it gets full. Okay. So if we were searching for 31, we'd come in here. It's not open. It's not 31. Go to the next. Not open. Not 31. Go to the next. Go to the next. Go to the next. Go to the next. Oh, found it. Return true. Right, so it's an order n search. Right? Even if you find it, it's gonna. If you have a billion elements, you might have to go through all a billion to find it. Okay, so this is something called linear probing. Okay. Then I don't usually write hash tables this way, in part because you have to maintain these bit fields, and like if you delete something, then how do you, you like erase it, but now I can't find 31 anymore. You know what I mean? If I were to set this to open, now when I search for 31, I come in here, not open, not 31, go here. Oh, it's open. False. But no, it's not false. 31's in here. And so handling deleting is kind of annoying. Like I said, with most data structures, handling deleting is annoying. So what you could have is another bit field that holds whether it's been deleted or not. You set that to true. So now every time you go through it, you say, has it been deleted? Is it open? Is it a match? You do all 3 of those checks for every element in the link in the hash table. And it's just kind of annoying to implement. It's kind of wasteful of memory, and it's kind of annoying to code. This is typically what most professors teach as the first hash table. I actually think it's more complicated than the one I'm about to show you, which is hashing with chaining. Linear probing is actually faster than this at low loads. So at low loads, load is the percent full, right? At low load, linear probing is better. With a high load, hashing with chaining is better. Much, much faster. Because linear probing turns into order n, worst case. Hashing with chaining, the way I'm going to show you, turns into order log n for insert, search, and delete. So linear probing, if you have, so here's the thing. Big point, big brain. Here's the main reason. Here's why you use hash tables and why hash tables are cool and what's the downside of hash tables. Hash tables allow you to throw RAM at a problem. Okay? Why did this performance get to be so bad? It got to be so bad because we ran out of room in our hash table. What's the solution? Throw more RAM at it. If I threw a gigabyte of RAM at this problem, these guys are going to be scattered over a giant swathe of empty space, right? They're not going to be, you know, bulking up into these plaque deposits of collisions all hitting each other, right? Because like if I were to insert 61, comes in here. If I were to insert 101, then it goes blah, 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 and all these collisions sort of build up on top of each other. And it gets just worse and worse and worse. If you look at the running time of it, based on the load, the running time of linear probing is like pretty good, and then after it gets towards about, I don't know, like 80% full, then it goes like this, whoop. And so linear probing is like good as long as you've got plenty of free space in the hash table. But then as the load factor goes up, the running time of linear probing goes to hell. It gets really, really bad. And so the solution is throw more RAM at it. Download more RAM. If I could take a hash table that's 90% full and double the size of it, now it's down to 45% full. And I've sped it up by a factor of 5. And if that's still not fast enough for me, I'll double the amount of RAM again and get it down to 10, you know, get it twice as fast. And so here is the big picture idea for hash tables. The big picture idea for hash tables is RAM equals speed. Okay? That's a really nice property to have because RAM is cheap. If RAM wasn't cheap, we wouldn't use hash tables nearly as often. Right? So RAM is cheap, and so you can speed up a hash table just by making it bigger. Okay? So let's talk about how I actually do hash tables when I write hash tables. Okay? And this is the way that Java does it, incidentally, by the way. So it's called hashing with chaining. The way that you'll see it in the textbook sometimes will actually be order n. I don't like order n. I like order log n much, much better. And so I'm going to show you the log n way of doing it. Okay. So you guys want to see me write a hash table from scratch? Hash browns, covered and smothered. Okay. For doing input, I'll include the binary search. What? Binary search trees. I thought you were doing hash tables. You'll see. And I'm not going to include unordered map or unordered set because I'm actually making a hash table. Okay. So let us make a hash table. Class hash. Don't call it lowercase, by the way. That will actually. There's actually a std hash. That's another reason why I capitalize my things like that, so it doesn't conflict with any standard library classes. Type like it's a competition. Oh, okay. So we're doing competitive coding now, huh? No. Everybody fire up TypeRacer. No, I'm kidding. All right. So while true. All right, so let's just do a little menu real fast. Int choice is equal to read. 1 insert, 2 search, 3 delete. Okay, so we'll read in 1, 2, or 3 if choice is less than 1 or choice is greater than 3. Quit the program. All right, so if choice is equal to 1, we're going to have a hash table here. Hash table called H. I'm sorry, naming variables is hard. Okay, so if choice is 1, then we are going to say h.insert. What are we going to insert? What type do you guys want to insert? Names, ints, doubles. What do you feel like? T. Template class T. What do you guys want T to be? Into, nouns, bool, ints. A hash table of booleans is very easy. Have you ever seen a true before? Yes. Have you ever seen a false before? Yes. All right. There you go. Hash table booleans would be very easy to write. Ints, fine. Okay, we'll do ints. Okay, make a hash table of ints. All right, so we're gonna insert a. Look at why the read library is so nice. You can actually embed input into a function call. So read type an int to input. Okay, so we're going to call h.insert. So privately, we're going to have a vector of sets table, and then publicly, we're going to have a default constructor. Does absolutely nothing, and we are going to have 3 functions on it called insert, search, and delete. Void insert, which will take in a type t named x, and that will okay, fine. We'll include vector as well. Sure. Now let's use an array. We haven't used arrays in a while. No. Array of it's negative size 1,000. We should probably static constant size. Don't like it. Oh yeah, it needs to be a set of type T. Okay, so I am making 1,000 binary search trees. Huh? Yeah. I'm making 1,000 binary search trees. I have an array of binary search trees of type int, t. Okay? So I've made an array of binary search trees. All right. So we need insert, we need search, we need delete. All right. Void and a Boolean search. Searching for x. And again, that probably should be const reference. I don't care though. All right. We'll do that later. And then void delete. I can't call it delete. Brace. There we go. There's our interface done. Down here in main, h insert read type int input. Choice is 2. So if the option is 2, type in an integer to search for. Yeah, I know I'm not returning anything, and I can also name this no discard. That. Oh, what is that? Muya, have you ever seen no discard before? What the hell is that? That means don't ignore the return value of this, right? So, so let's get this guy to shut up about not returning value. So if I have a function that is called search, and it's going to be returning true or false, and you don't do anything with the return value, then your code's probably wrong. You know what I mean? Like, what's the point of searching for a value if you're not going to do anything with it, right? It doesn't do anything. In fact, this should be a const function, right? Now look down here. You guys see this line down here? Everything's compiling fine. No warnings. Watch what happens when I make it no discard. Did you guys see that? And let's make this a const function as well. Why not? So, because I marked it as no discard, that's called an attribute, by the way. An attribute, double square brackets is an attribute. It's a compiler thing that it looks at. The compiler now looks at this and goes, bro, this is marked as no discard. You're not supposed to ignore the return value of it. You got to catch it. You got to catch that value. Don't let it get away from you. So bool retval equals hsearch. And then it goes away. Thank you. Let's wait for a second. Right. So if you have a function where you absolutely positively, there's no point to the function if you're not looking at the return value, you mark it as no discard, and then it'll warn if you don't catch the return value out of it. Sometimes people will mark things as no discard that shouldn't be. For example, the system call that runs a Unix program, it's marked as no discard, which is super annoying. Because if it didn't work right, I don't care. The return value is just the error code. I don't care. The main point of running system is to run the thing. And system is marked as no discard. And so you have to catch the return value, or the other way of doing it is to mark it as cast it to void or something like that. Cast it to void, and then it'll ignore the no discard that way. But you have to explicitly be like, yeah, I don't want it. So that's a cool thing. That's a cool thing. Yeah, if you output it, sure. But like, let's say you actually don't want the return value. Like for system, I don't care about the return value because the point of system is not the return value. It should not be marked as no discard. This one, the only thing that search does is return true or false. So if you're not catching the return value, that's a problem. Okay. So down here, I will just be like, if ret val, see out. Yep, it's in the hash table. Otherwise, see out. Nope, not in the hash table. Okay, so all right, and then finally, if make this an else, why not? Elsa. Shut up, dude. COC, stop flipping out, dude. Have some chill. Just wait for me to make a mistake. All right. So otherwise, we're going to delete. So we will call h.delete, embedding in h.erase, embedding inside of it. Read. Please type an int to delete. And there we go. There we go. That's main. You notice how compact it is when you use the read library. It's way more compact. And you can embed your IO stuff inside of a function call. Cool stuff, right? All right. So here we go. Let's do a hash table. Got main done. We got our interface done. And this is where you should always start. You should always start with like some stubs like this and a little driver in main. You can stub it, you can driver it, whatever. Either way, you know, start off by getting something working. You should always have your code working, right? And in fact, if I had time, I'd compile it and run it and verify that it did absolutely nothing. So let's do this. So how do we insert into my hash table? All right, well, maybe I don't want to template it. I would have to add in a check if I really wanted to do this correctly, or I could call the stat hash function. I'm not going to worry about it for now. I'm writing bad code. Just be aware of that. Okay. So I'm just going to take x and modulus it by size, and this is going to be the bucket number. So this is going to be int modulus. Int. Okay, so the answer is going to be an int bucket is equal to that. If while bucket is less than 0, remember modulus will sometimes give you a negative number if you pass in a negative number, which is wrong. While bucket's less than 0, bucket plus equals the size. We'll bring it up into positive territory. That'll give us the right bucket. All right, so bucket is modulus size. And then we are going to, at that bucket, we are going to insert it into a binary search tree. So what we're doing here is we're making a hash table of binary search trees. So we're doing hashing with chaining here because it's easy to write. It's faster in most cases. And so we've got our buckets. And so if we were to insert 51, 51 would go into the binary search tree here. What? Binary search tree. Yep. And then let's say we insert 61, hashes to bucket 1 also. So we got a binary search tree growing out of a hash table. We're compositing data structures together. What? You can do that? Yep. 11, insert 11, then the binary search tree in bucket 1 gets 11. Let's insert 21. 21 goes to bucket 1, less than 51, greater than 11, like that. And so we have an array of binary trees. And so if the hash table is mostly empty, you're going to get order 1 insert search delete, which we want. But as it gets full, worst case scenario, all of the elements map to the same bucket. So worst case scenario, it's just a binary tree. It's just a binary tree with more steps, right? So we get 61, 71, 81. Yeah, okay. So there's no 1 between these two. Okay, so do you guys understand? So it is a hash table of binary trees. And so what we're going to do is just say table square bracket bucket dot insert x. Cool. Let's make this. Let's actually make this a hash. That's not called hash. I can't come up with a good name. Hash. Let's call it hash. Okay. One line of code. Because we're going to be doing this hash function we're going to be using over and over again. And that's what that's going to do. It's going to give us a value between 0 and 999. So if they pass in 1001, 1001 is the value that's getting inserted. 1001 modulus 1000 is 1. So the bucket's 1. It's not less than 0, so it returns 1. And so we can actually just embed that hash into the table access and be done. For search, return converting to bool, table square bracket hash x dot count. You don't like it? You don't like it? Gotta make it constio. All right. Nope. Yep. Nope. Reference to non-static. There. Count the number of x's in it. Yep. All right, so it's going to count how many times x appears in the binary tree that x should be in. I convert it to a bool, which it would pretty much do anyway. And then for erase, we are going to say table square bracket hash x dot erase x, and we're done. That's a complete working high-performance hash table. Not super high performance. There's higher performance, but it's fast enough. It's pretty fast. Worst case, it just is a binary tree. Worst case, it's a binary tree. Login performance, still pretty good. But if the size of the thing is bigger than the number of elements you're going to insert, then it will give you close to order 1 time. And as it gets fuller and fuller, it gets to order login time. Login is still pretty damn fast. So, yeah. Okay. All right. Yep. That's hash table. So I am not reallocating when it gets full. No, I'm not. So what I could do is make this a template parameter. And then when I make the hash table, this is probably a better way of doing it. Rather than making all my hash tables size 1,000, when I make it, I simply pass in, I'm probably going to have about 200 people inserted, so I'm going to make a hash table size 2,000. Just so I get the extra performance out of it. Right? Kind of like how the array works. So just make it a template parameter. then the person using your hash table can choose how much RAM they want to allocate. It's not going to reallocate. Like I said, there's more you can do, but I think that's pretty good. 3 lines of code, dude. Yeah. So, what do you guys think? I should probably run it. G++ hash browns covered and smothered. Let's see if this works. Insert 42. Search for 42. Yep, it's in the hash table. Search for 420. Not in the hash table. Delete 42. Search for 42. Not in the hash table. And we're done. Peace. Mic drop. So, yeah, that's a pretty good hash table, honestly. Honestly, it's pretty good. It's not, you know, I'm not going to, you know, the standard library one's better because it'll resize itself and it has all sorts of other bells and whistles on it. But, like, if I just needed to make a hash table for something, which I do, like, hash tables are my favorite data structure. Yeah, I can spit out a hash table in a couple minutes, you know. It would have been faster if I wasn't explaining what I was doing, you know what I mean? So that's some surprisingly compact code. Yeah, the reason why it's compact is because I have offloaded all of the nonsense on handling collisions. I've placed all of that burden on the binary search tree. Right? If there's a collision, it goes in the binary search tree. The binary search tree handles it. Rebalancing itself, all that stuff. Nope. I find the right bucket, dump it in. And so this will have better performance than a binary search tree when the when the table is mostly empty. So when the hash table is mostly empty, it's going to behave in order 1 insert, order 1 search, order 1 delete. And then as it gets fuller and fuller and fuller, it'll give you binary search tree performance, which is already pretty good. The linear probing that I showed you degenerates badly. So, yeah, okay, that's a good one. So, when you do linear probing, as the load factor is the percentage full, right? It gets bad, like right around 80, 70 to 80, 90%. It goes, and it just, zoop, it goes like that. So, linear probing is faster at lower load. And see, this is almost always more efficient. Nah, not true. When it's, because if you actually benchmark it, the linear probing is actually faster at load of 10. And the reason for that is because most of the time you're going to hash to a spot, be like, yep, there it is, return true. With open hashing, you hash to a spot, then there's a pointer. And you have to dereference the pointer and follow the pointer to the binary search tree and then be like, oh yeah, there it is, and it returns. So if you were to search for Jim here, there's actually 2 steps. You go to 1, then you go to the binary search tree. With linear probing, you jump to 1, you're like, yep, there's Jim, and it returns true. So at a low load, linear probing is actually faster. And if you have infinite RAM, which in a lot of cases we do these days, my boring PC here has 32 billion bytes of RAM in it. Like that's, you know, that's a lot. You know, maybe it can't hold the entire population of China, but if I'm doing something with the entire population of China in it, I can upgrade to 200 gigs of RAM, like not breaking the bank or anything. You know, it's not really that bad. I just kind of figured I don't need more than 32 gigs. And so if you need absolute performance, linear probing is actually faster. But it just has a really bad downside. The really bad downside is when it gets full, right? And so if you want maximum performance, you throw way more RAM than you need at it and be like, there you go, boom. I usually don't worry about it. Because like I said, handling, you know, when it's been deleted and handling if it's open or not, yeah. Give me that. Right? I can write this. That's 3 lines of code to do all 3 operations in order 1 time, basically. Right? It's pretty good. It's pretty good. So I will put this up in public for you guys, and you can admire it at your leisure. So copy hash browns covered and smothered into the public directory, and I will make it public. And that is our lecture. So the zyBooks, we're going to go over heaps next time. And so zyBooks will be on hash tables, I think, this time, and then heaps next time, or vice versa. Doesn't matter. But basically, learn hash tables. They're very important. They are my favorite data structure because they're the fastest at insert, search, and delete. And that's what I do most of the time. Okay. So have a good spring break. No homework, but homework if you want there to be. There's no pointer in the hash table. This is a pointer. That is an array of pointers. It doesn't look like it, but it is. So that is an array of pointers to the roots of binary search trees. It just looks nice. You don't see a pointer in there. Because no news is good news. I don't have a destructor. I don't have a constructor. I don't have a copy constructor. I don't have a copy assignment operator. None of that. It just works. Rule of 0, baby. Rule of 0. I don't have to write any of that. I can spit out an efficient hash table. All right. See you guys. Have a wonderful, wonderful break.